Ladies and gentlemen, welcome to day 2 of our work on verifying trigonometric identities. Alright, so today we're going to dive back in, we're going to do some more examples. Before we get into those examples though, I want to kind of put some of our strategies together, kind of like what we did at the end of the last video, so that you have somewhere to look if you get stuck. Okay, so the first or number one thing that I would tell you to always be on the lookout for is to substitute using identities. Alright? Identities. Substitute using identities. That's number one. Alright? Now the biggest one that we're going to use, and hopefully we're starting to memorize or understand how this works, is our sine squared plus cosine squared equals 1. Of course, from that we can get a couple of others. We know that we can write that as, excuse me, well, if we divide every piece by sine squared, we would get 1 plus cotangent squared equals, what's 1 over sine? Cosecant. Or, if we took the original and we divided by cosine squared, we would get sine over cosine. Okay, so tan squared plus, well, cosine squared plus cosine squared over cosine squared is 1, and then 1 over cosine squared is secant squared. Alright? So these are our Pythagorean identities that we use a lot, and just also be on the lookout, or please remember, you can write it in different ways, right? Like, I can write this as sine squared is equal to 1 minus cosine squared, or any other type of arrangement. Okay, so that's number one, being able to substitute using identities. Number two, something to always be on the lookout for, is factoring. Factor. Things to keep in mind, well, GCF. We can always do our, what is it, A minus B, A plus B type situation, etc. Alright, so we always need to be on the lookout for factoring. Kind of going along with factoring, but reverse, is multiplying by a conjugate. Alright, multiplying by a conjugate. That sometimes will help. What does that look like? That means, well, if I have 1 minus sine of theta and 1 plus sine of theta, we'll say that those are the conjugates. Our conjugates. Just for a little note. What am I missing here? I'm missing a couple. Oh, a huge one. Writing in terms of sines and cosines. Alright, now this one, I want you to understand that if you can turn 6 trig ratios into just 2, things are going to cancel out a little more. Okay, so seeing secant, cosecant, tangent all in the same, well, it's easier, or not, maybe not easier necessarily, but we can start to see if things cancel out if we get them all in terms of sine and cosine. Now the last one that we definitely need to keep in mind is common denominator. Alright, so here are some strategies, things that we can use to help us simplify or verify trig identities. Now, I will say, these first couple of examples, or first few maybe, when we use the word simplify, I tend to think these are more difficult than verifying. And I think that because I'm not giving you an end goal, right? Like, think of a proof from geometry. What if I just gave you a bunch of givens and then never told you what to prove? You could do so many different things with it, right? There's no direction. So what I really want you to do here is I want you to just start simplifying as best you can using our, oh, I'm pointing at something you can't see, using our rules or our steps and see where we get to. Okay? So hopefully when we look at something like number 1, well, I see a sign here, I see a sign here, so there's not really a reason to do any like changing to cosines or different types of ratios. But we know that we can factor. All right, and so when I see sine x minus sine cubed x, I see a sign in both pieces, which means I want to take out a GCF of sine x. And when I take a sine x out of sine x, I'm left with 1. And when I take a sine x out of negative sine cubed x, I'm left with negative sine squared. And this is nice because now, and again, we're going to practice this, but hopefully we see something that's starting to look familiar to us. All right, 1 minus sine squared. If we go back up, or if we have our Pythagorean identities next to us, what if I had solved for cosine squared? I would have had to move this sine squared over to the one side, right? I would have had to subtract it. So cosine squared is equal to 1 minus sine squared. And that's what I have right here. I have a 1 minus sine squared. So this just means that I'm going to replace cosine squared x with, replace 1 minus sine squared x with cosine squared x. Now, that looks pretty simplified to me. I can't write cosine in terms of sine, so I can't cancel anything else out. Yeah, this looks as simplified as possible. Okay, so we are done. And my bad, I probably should have been putting equal signs. I'll get better. Okay, as we move on to number 2. This is a great example of when we see multiple types of trig ratios. Sometimes it's better if we write them in, or write all of them in terms of sines and cosines, right? I don't know how tangent works with secant necessarily, but if I can turn some things into sines and cosines, that might help us out. All right, so let's see what happens when we do that. I'm going to put my equal sign right here, actually, and I'm going to work right off of it. Well, sine x is already a sine, so I'm not going to change that. But I do know that I can rewrite tangent, and again, multiplication, right? There's a multiplication sign there. So multiplied by, we know tangent is sine x over cosine x. That is one of our quotient identities. Let's see what else. Oh, we also have a minus secant. Well, minus secant is 1 over cosine. All right, this is starting to look better. I think there are some things that I can do here. Okay, let's see. Well, I know that this is multiplication, and when I multiply fractions, I just multiply across the tops and across the bottoms. So this sine x times this sine x is just sine squared x, and that, of course, is all over cosine x. And then I still have my minus 1 over cosine x. Well, this is great. I don't even need to get a common denominator. I already have a common denominator. So I can just keep going, and I can say that this is sine squared x minus 1 all over cosine x. All right. Now, when we look at that numerator, I'm hoping that we're starting to see, especially because of that squared, that we can do something with this. All right. We can do something with this. What I will do, and just to kind of show you guys, because it's really important that we get the signs and like plus, positive, negative right, I'm going to rewrite my Pythagorean identity over here. I'm going to work off of it. Okay, so I have sine squared x plus cosine squared x equals 1. Now, I have cosine squared x minus 1. I want, oh, you can't see what I'm doing, okay? I want to get this to look like sine squared x minus 1. So that means I'd have to move this 1 over. But then, of course, what would I have to do? I can't have the cosine squared x with the sine squared x minus 1, so I need to move this over. So I'm going to end up with sine squared x minus 1, right? I move the 1 over. And then I have to move the cosine squared over as well, so negative cosine squared x. And now I know that because these two things are exactly identical, I can replace or substitute. So negative cosine squared x all over cosine x, and I really, really hope you guys know what to do next. If I have cosine x times cosine x, right? Cosine squared means I have 2 cosine x's on top and 1 on the bottom. Well, then I can cancel one of them out. which means that my final answer should just be negative cosine x. Okay, so this used a couple of strategies. It used changing things into sines and cosines, and it used our Pythagorean identities. Let's keep going. Up at the top of the next page is an example of factoring, and I know it's goofy looking, but we can factor this. I don't know if you guys remember from when we were doing exponentials, but we used a strategy called a substitution. And I'm here to say that you can use a substitution again if it helps you. What I mean by that, what I mean by that is some people have a tough time seeing that this is really cosine squared x and this is cosine x. All right. So if I set a equal to cosine x, and then I do some replacing, well, cosine squared x then is a squared plus 2a plus 1. And I know how to factor this. This is a plus 1, a plus 1, or a plus 1 squared. So the very last thing that we would have to do is just remember, I don't want a's. What was the original? It was cosine x, so we plug the cosine x back in. All right, and we're done. We are done with this. This is as simplified as this expression can be. Okay, now for my favorites, the verifying or establishing the identities. I don't know why, I just really like these. They're kind of like little puzzles to me. Don't make fun of me. Anyway, yeah. So things that we need to remember in order to establish the following identities, we remember choose more complex side to start. All right. So hopefully you agree with me. The left side here is way more complicated or way more complex than the right side. If I tried to start with cotangent squared, I wouldn't know what to do. I wouldn't know if I should use my reciprocal functions. I wouldn't know if I should use my my quotient identities. I said reciprocal functions. I mean reciprocal identities. I wouldn't know if I should use the Pythagorean identities. Okay, so start with what's more complicated. It's going to be easier to kind of see the pathing if you start with the more complex side. So I'm going to do it. Left-hand side is cosecant theta minus 1 and cosecant theta plus 1. All right. Well, let's see here. What could I do? Could I distribute? Yeah, let's do that. Let's see what happens when I distribute. If I distribute, I get cosecant squared theta, and then the insides and the outsides cancel, and so I just have cosecant squared theta minus 1. Okay. If we go back to our identities, and I look at the one with cosecant squared, well, what could I do right here to get cosecant, or to get this in green, to look like this in red? Well, I could move the 1 over. So cosecant squared x minus 1 is actually equal to cotangent squared x. So guys, I'm actually done already. I know that this identity leads me to cotangent squared theta, and I am done. All right. Now, for number 5, I want you to do this. Try to split your paper here. I'm not going to say it's going to be perfect, but I'm going to ask you to try a little more after the video's over to see if you can do the problem kind of the backwards or opposite way and get to the same answer, okay? So what we're going to do here on the left side is we're going to say that cosecant minus cotangent is the more complicated side. All right, we're going to work off of cosecant u, cotangent u. And then for homework, or for you to finish up after, I want you to see if you can work off of the right side to get to the left side. So, left-hand side, cosecant u minus cotangent u is what we're starting with. And let's see here. I know cosecant, cotangent, I really don't like using those, so I'm going to see if I can convert into sines and cosines. Well, cosecant is 1 over sine, and cotangent is what? Cosine over sine. Okay, this is looking good. I know that I have a common denominator here, so I can just put them together. 1 minus cosine of u over sine u. Interesting. This is interesting. When I look at this, I see that I have cosines in the numerator, sines in the denominator. But in what I'm trying to get to, my goal, I have sines in the numerator and cosines in the denominators. So things are a little goofy right now. What I want you to kind of keep in mind here, when I see this 1 minus cosine u, a lot of the times the trick is going to be multiplying by the conjugate. And why is that? Well, I want to get a cosine into a sine. And the way to do that is using our Pythagorean identity, right? If I have sine squared, then I can get cosine squared. Or if I have cosine squared, I can get to sine squared. So what we have to do, though, is we have to get this into squareds, I'll call it, right? There's no relationship between cosine and sine. There's relationships between cosine squared and sine squared. So again, the trick here is to say, well, if I want this to become sines, then I have to multiply by the conjugate. And if I do it to the top, I got to do it to the bottom. All right, so when we keep going on this, well, 1 times 1, so we have 1. Inners and outers will cancel, right? That's why it's minus plus. And then, of course, this will be 1 minus cosine squared u. And then if you remember from the video, I would not distribute this. I would just leave this as sine u 1 plus cosine u, because we're hoping something else is going to cancel out. And let's see if it does. Well, using our Pythagorean identity, we know that 1 minus cosine squared is just sine squared. Oh, this is looking good. I bet you guys can see it now. What's going to happen? Well, I have cosine squared in the numerator. Did I say cosine? I meant sine. Sine squared in the numerator, 1 sine in the denominator. Boom, boom. And so, of course, I'm left with sine u over 1 plus cosine u. And what do you know? That's what we wanted. Okay, so this was, again, just some more practice problems, some different types of problems, so that you can start to kind of see the process of simplifying and verifying trig identities. For homework, I'm going to ask you guys to do one more thing. I want you to see, and we'll check tomorrow, I want to see if you can start with the right-hand side. All right, right-hand side is sine u over 1 plus cosine u. I want to see if you can get to the left-hand side if you start with the right. All right? And again, this is the reason I'm asking you this. These are both pretty complex, right? This is 2 terms. This is actually kind of like, well, I guess it's still only 2 terms. But it's a little more challenging to decide which side to start from. And I want you guys to see that it doesn't matter. You can start on either side, and you should still be able to verify. Okay? So, that is it for the video. I hope that you guys are starting to see how some of this is working, and I hope that we practice more tomorrow in class. All right, later.